Hello students. So we are into chapter 5. Okay. So last lecture we saw the response of a first order system to unit impulse to unit step and ramp input. Yeah. Today we are going to do the same thing. However, we will be doing for the second order system. Second order system. Okay. For first order system, the differential equations as we studied, right? Cx dot plus kx equal to f. This is the first order system. Okay? First order system. And what we did, we took the Laplace transform in this ft. And we got the transfer function equal to xs equal to fs equal to, we get 1 over cs plus k, right? So this is how this is first order system. Yeah, so the first order system is spring and damper system. That's it. K, C, this is ft, like this one. Second order system we studied already. Yeah, so in the vibration part, what you're going to do, you add mass there and then you are into the second order system. And the equation for this one, we know that equation is mx double dot plus cx dot plus kx equal to ft, and you are taking the Laplace transform of that, and what you get is ms square plus cs plus k xs equal to fs, and t is transfer function of that xs output over fs input equal to 1 over ms square cs plus k. Yeah, that's what you got. Okay. Now these are the mechanical system, the vibration system that we have studied already. Yeah. The other examples will be, for example, you have a motor control, right? So you have a motor and the motor is driving a load or flywheel. Let us say this is J, and what is the motor? We are not looking at the motor, we are looking at the torque. Yeah, so this is torque, and this is a flywheel, and there may be, so the axle may have some bearing. Because of that there may be friction. Yeah, and the air friction may also be there. So because of the friction, equation becomes, as we have seen earlier, equation will be tau, right? So tau is the tau which is acting, tau, and will be equal to j theta double dot plus b theta dot. So this equation we already derived. So this is the mass moment of inertia, and this is equivalent to the damping. So this is the damping coefficient for rotational motion. This is rotational velocity here. Their rotational acceleration is there. This is mass moment of inertia. This is tau is the torque. This has the form of something like this: mx double dot plus cx dot, but there is no k term here. Yeah, so there is no k equivalent term here, but this is also a second order system. Second order system because if we take Laplace transform, we get tau s equal to j theta s plus b, we get js square plus bs multiplied by theta times s. If this is the input and theta is output, what do we get? We get Ts equal to theta s over tau s equal to 1 over js square times ps. Yeah. So this is also a second order system. Although there is a difference here, we have k here. There is not k term is not there. Yeah. But if you have a feedback loop, let us say if you have this kind of system where you have this system meaning that this is the flywheel that represents it, and here you have 1 over js square plus ps, and let us say if you close it like this, you may have some, let us say, some controller here. Yeah, so controller having a gain here, and you have like this, so plus minus plus, here you have reference rs, and from here you are going like this output like this. So this is cs. If this system is like this one, then feed forward transfer function becomes simply k over js square plus bs, and the closed loop system, the closed loop transfer function will be simply, you will have k over js square plus bs divided by 1 plus the feedback transfer function, which is 1, multiplied by the feed forward transfer function. Yeah, so this becomes a k js square plus bs. Yeah, okay. So we get ts equal to, multiply like this one, we get k over, we get js square plus bs plus k. Yeah. So you get this kind of transfer function. So which is equivalent to similar to this type, right? Yeah. Okay, so this transfer function ts equal to k over js square plus bs plus k, we can write it as the way we understand, and divide by j, for example, k over j, so it becomes x square plus b over j plus k over j. J is equivalent to mass, right? And this k we can take it as the stiffness. So this becomes simply, this is omega n square, you know already, s square. This is will be s. So b over j, you can write it at 2 zeta omega n s, and plus you have omega n square. So we can write it like so. This is a standard form, you know. So ts equal to omega n square over s square plus 2 zeta omega n s plus omega n square. So this is the standard 2 degree of freedom transfer function, and we understand already the meaning of omega n. What is the meaning of zeta? So from second order system or the spring mass damper system, we know what is, this is the damping ratio, this is the natural frequency, and the same kind of word we also use it here, although this is not about the actual the spring mass damper system, but equivalent system which actually has a similar transfer function. So here we can write as omega n square equal to k over j, yeah, and 2 zeta omega n is equal to b over j, right? So we are getting from here, right? Okay, so the way there we wrote, so here in a spring mass damper system, how you wrote? We wrote omega n square equal to k, this is c, so k over m, and zeta we said c over root 2 km. Similarly, we can write it here. So here your zeta is equal to c and b are equivalent, so write b over root 2. K is big K here, km is z. So zeta in this case is b over root 2 kj. Yeah. So always whatever you studied in a spring mass damper system, you can apply it here. The same meaning basically. Yeah. So here also the system will be vibratory only. Yeah. So because the transfer function is like this one, if you give input, step input, there has to be some vibration provided the parameters are right, provided this is underdamped condition. This may be wrong, so we can check it also. So okay, so whether this will be here or there. Okay, so I may be wrong, so let's check it. So this omega n square, with this we know, right? So omega n is equal to k over j, and square of this you do it 4 zeta square omega n square over b square over j square. So we divide by this one, so we divide by omega n square, so divide by k over j, and what we get, b square over j square multiplied by j over k, and what we get b square over kj, right? Okay, so and that is equal to 4 zeta square, and hence zeta equal to b over 2 kj. Yeah, so it should be 2 should be outside here. Yeah, so this was wrong. So this is the okay. So what we get omega n square equal to k over j, and zeta is equal to b over 2 root k. Okay, so these are the correct one. So correct. So 2 should be outside, not here. Okay. Next thing is you should remember that we, depending on the zeta, so we have the zeta equal to 1, we call it critically damped. Zeta equal to 0, we call undamped. So this is just a repeat. Less than 1 but greater than 0. Yeah, so you call it underdamped. Okay, and then zeta greater than 1 is called overdamped. Yeah, and all these conditions we have already seen, so you know what is the meaning of that. Yeah, so for then when zeta equal to 0, for example, and then what happens, this becomes ts. So let's take zeta equal to 0. Yeah, so which is undamped, and you get ts equal to omega n square over s square plus 2 zeta plus omega n square. Yeah, and what do you get? This is a form of the, if you for a step input, for example, if you want to study, what kind of output you get? So you can remember basically this is equivalent to you can assume this is as a force. Yeah, so this is being as a force, and which may be given constant for you, and this is the mass. What you get here is the, based on that you can find out the inverse Laplace transform. You will get sinusoidal output, meaning that if zeta equal to 0, for a step input there will be a sinusoidal output. So let us say, or for a unit impulse. So, unit impulse, for example, if you want to study, if you give unit impulse and you want to find out how it will look like, So unit impulse, then Ts equal to Cs over Rs. Yeah, for unit impulse, that means RT equal to RT is equal to like a delta direct function, right? So is delta t, right? That's what that is, right? Okay, and hence the Rs is equal to 1, and hence that tells you CT equal to Rs equal to 1, so L inverse Ts times Rs, where Rs equal to 1, so L inverse Ts, okay, equal to L inverse omega n square over s square plus omega n square. Yeah, and that will be equal to, so omega n. So here you can have omega n here, omega n outside L inverse omega n over s square plus omega n square, and that is equal to omega n multiplied by, this gives you sinusoidal, right? So sine omega nt is the answer. So what we got is we will have the purely sinusoidal output in this case, omega n multiplied by sine omega nt is the answer. Okay, now we have to study how it behaves under the step input. Okay, so step input, response to the step input is very important. So that's what we will do. So you know how to find out for different kind of input what is the output, as we have done for first order system. For second order system, you can do exactly the same way. Yeah, so second order system, as we learned that the standard format will be something like this one, s square plus 2 zeta omega n s plus omega n square. And for general case, we want to find out the step input. So meaning that this is equal to, we call it, is equal to Cs over Rs. Okay. And now Rs, a step input. A step input, when you say, that really means RT is equal to 1. Yeah, so it is like T, and from here it is 1. Unit step input. We want to find out what is the response to that. Yeah. Okay. Now that means Laplace transform Rs equal to Laplace transform RT equal to Laplace transform of 1 or unit function O. So this becomes 1 over s square, 1 over s, and hence the Cs equal to Rs times Ts, and Rs equal to 1 over s, and Ts is omega n square plus s square plus 2 zeta omega ns plus omega n square. Okay, so this is Cs, and hence Ct will be L inverse omega n square divided by s times s square plus 2 zeta omega ns plus omega n square, right? So this is what the step unit step response for the system. And which system we are talking about? This is a standard second order system. Yeah, you write like this. Okay, now this in order to find out what do you first, you basically you can write L inverse, and then you write in different format meaning that here you write A over S plus, you can write B, not B, even we can write C and D. Okay, C S plus D divided by S square plus 2 zeta omega ns plus omega n square. So we write like this. Okay. Okay, so L inverse, and we have A S square plus 2 zeta omega ns plus omega n square plus CS square plus ds, and divided by, we have this S square plus 2 zeta omega ns plus omega n square. Yeah, and hence omega n square is the constant, so what we get, A times omega n square equal to omega n square. That tells you A equal to 1 simply. Yeah, and hence we can find out C equal to S square, whatever the C and S square here. So should be 0. So A plus C equal to 0, hence C equal to minus 1. Yeah, and then we have 2A zeta omega n is plus D equal to 0 and D equal to minus A equal to 1, so minus 2 zeta omega n simply. Yeah, so that really means we have CT is equal to L inverse, and we have A over S, where A is 1 over S, plus CS plus D, where C equal to minus 1 and D equal to this one. So we can write minus CS. So C equal to minus 1, so we just have S. Yeah, and D is plus 2 zeta omega n divided by, and you have this one, S square plus 2 zeta omega n plus omega n square. So we get this. So answer we get equal to L inverse 1 over S. Now 1 over S is 1 only, right? Or right, so, and then we have L inverse of the whole thing, this S plus 2 zeta omega n divided by S square plus 2 zeta omega n plus omega n square. Okay, so as we know, there are 3 conditions, right? So we have first condition, which is underdamped, and underdamped zeta is less than 1 but greater than 0. And if you have that, then we can write CT as equal to 1 minus L inverse, and we have first, we can write this one as follows: S plus just write zeta omega n plus zeta omega n. Let's write this one divided by, and here we will have S plus zeta omega n square. Yeah. So all these things we have done already earlier, so we are just revising it. So S plus zeta omega n square, and we have done during the vibration lectures. So we have S square to zeta omega n plus zeta square omega n square. So we write minus zeta square omega n square plus omega n square. So that's what you get here, right? Okay, and will be equal to 1 minus, okay, so we get L inverse and S plus zeta omega n, so we can split into two. So one will be S plus zeta omega n divided by, and here we get S plus zeta omega n square, sorry, zeta omega n square plus omega d square. Remember we had omega d earlier, so same omega d square, and plus zeta omega n divided by same thing, S plus zeta omega n square plus omega d square, where omega d square equal to omega n square 1 minus zeta square. So like this, yeah, or omega d equal to omega n multiplied by 1 minus zeta square. So like that. So next we can write Ct equal to, we have 1 minus the first part. So Laplace transform of S plus zeta omega n over this one. This will give you the value of is cos, you have S plus zeta omega n terms, so you have e to power minus zeta omega n multiplied by this S over, so that's why you will have cos omega d t. So this you get from this, and from this one you have zeta omega n divided by S plus zeta omega n square plus omega d square. So we have to have omega d here, so we can write minus L inverse, and then we write 1 over omega d multiplied by zeta omega n over omega d, and then you have omega d over S plus zeta omega n square plus omega d square. So Laplace transform of this. Yeah. So next we have 1 minus e to power minus zeta omega n cos omega dt minus, so this you can take outside, zeta omega n over omega d, and this one inverse Laplace transform of this part will give you sine. So this is sine omega d t, not only sine, there has to be e to the power. So S plus zeta omega n, so that means e to the minus zeta omega n. T term has to be there, so t like this. Sorry, so here also t term has to be there. Okay, so minus zeta omega n t, and then you have sine omega d t, where omega d equal to omega n times 1 minus zeta square. So this what the Ct you get. Okay, you can simplify further. You can say 1 minus e to power minus zeta omega n t. You can write it as a common thing, and then you have cos omega dt minus, now you can spell out here omega d, it has zeta here and omega n here. This is omega n root 1 minus zeta square here, and then you have sine omega dt like this is equal to 1 minus e minus zeta omega n t, and here we can write the term here. We have 1, but the whole thing we can write as values, let us say A sine omega d t minus phi. Yeah. So we can write something like this one. Okay, where we have to find out what the actual value of these are, and the value here will be, so here we have cos, so basically what we will get here is minus may not be there. Let us see. So here we get a sine here, we want to have a cos here basically, or and here we want the we will have the sine term. Okay, so either we can write it as we can take minus that side as well. So actually we did some mistake, that's why this confusion is, we have minus here, so we have minus here, so we should get a plus here, you know. So okay, so if you have plus here, so let's write this equal to plus. Okay, so we have plus here. Now this is clear, yeah, so there's no confusion now. So this we can write this way, and in that case we can write where this is sine, so this will be cos, yeah. So where A cos phi is equal to zeta omega n over omega n. So basically simply this you get zeta root 1 minus zeta square, yeah. So this is A cos phi, and A sine phi will be simply equal to 1, right? So A sine phi equal to 1. So you get tan phi equal to root 1 minus zeta square over zeta, yeah. So this is phi, that really means phi equal to tan inverse phi, yeah, sorry, tan inverse root 1 minus zeta square over zeta. That's what we get. Yeah. So let us see if it's correct. So we have sine here, so if you are writing sine, so it has to be cos here. So A cos phi equal to this, it will be sine, A sine phi equal to a, so we get like this one. Okay, so final form we can write Ct is equal to 1 minus e to the power minus zeta omega nt, and we have with that sine and then sine omega d. So omega d is nothing but omega n root 1 minus zeta square t, and then plus tan inverse root tan inverse root 1 minus zeta square over zeta. Here also we have to write something, and that will be, that tells us that A is nothing but equal to is this square plus this square. So basically zeta square over 1 zeta square plus divided by 1 minus zeta square plus 1, and that means simply 1 over, so 1 over 1 minus zeta square, yeah. So that really means here we have to multiply 1 over root 1 minus zeta square. So Ct equal to 1 minus e to power minus zeta omega n t, yeah, let's write like this, multiplied by 1 over 1 minus zeta square, right, times, so this is 1, okay, multiplied by sine omega n root 1 minus zeta square t plus tan inverse root 1 minus zeta square over zeta. So this is the final form of Ct. Now RT error we have to find out. So ET equal to RT minus Ct, and RT was 1 minus 1 plus we have e to the y minus zeta omega n t over 1 minus root 1 minus zeta square, and you have sine omega n root 1 minus zeta square t, right, plus tan inverse root 1 minus, so let's write here, plus tan inverse root 1 minus zeta square over zeta, like this. So 1 cancels out, so this is the error. Now a steady state error, right, a steady state error, if you want to find out, how do you do? It has to be at t infinity, right? So ESS in this case will be at t goes to infinity, what value we get. So this becomes e to the power infinity, thus becomes 0, right? So this value becomes 0 basically, right? 0, and multiplied by what you get here, whatever you get, right? So becomes 0. So in this case, the you are giving the step input, and in long run the value becomes 0. For undamped conditions, yeah, so for undamped condition zeta equal to 0, you can put that value. In that case, E steady state will be zeta equal to 0. Yeah, so to begin with your zeta equal to 0, it becomes 1. So you get simply this becomes 0, 1, this becomes also 1, and here you have omega nt, so you get equal to sine, right, you get sine, and you get omega n t plus tan inverse, and you get tan inverse, so this is basically pi over 2, right, root under 1 minus zeta square over 0, so 1 minus zeta square, so 1 over 0, so this becomes actually pi over 2. Yeah, so the value is oscillating basically, so what you get is equal to this one. We can also, it will be equal to cos pi by 2 minus omega nt minus pi over 2, which is equal to cos omega n minus omega nt equal to cos omega nt. So steady state error is never 0, so this becomes a function of time. Even if time tends to infinity, still you cannot take a limit of that, so this is actually oscillating. So in long term, steady state is 0 when undamped condition, when zeta equal to 0, there will not be steady state error, will not be 0. Yeah, so that's what it tells. Okay. So we have seen so far the underdamped condition, and undamped condition and underdamped condition. Undamped condition and underdamped condition. So this is the original CT which is applicable to all of them. Now let's say we want to look at the critically damped condition. Yeah, so in that case we have zeta just equal to 1, and if we put it the value here, so zeta equal to 1, and what we get simply is CT is equal to 1 minus L inverse, and you get values L inverse, and then you get S plus 2 zeta omega n divided by zeta equal to 1, so you get 2 omega n simply, S 2 omega n divided by S plus 2 omega n plus this S squared, there has to be S value here, so S squared plus 2 zeta omega n S. So here also there has to be S value. So please correct it in your notes. Earlier we forgot, we had to be 2 zeta omega n S here also. So S plus 2 omega n divided by S square, S plus omega n square. So we can have this. Yeah. Okay. So if you take the, so we get equal to 1 minus L inverse, and then you have S plus omega n, right, divided by S plus omega n square, you get 1, and then you get minus L inverse omega n over S plus omega n square. So we get 2 of them like this one. Hence we get 1 minus L inverse 1 over S plus omega n, right, and we get here minus L inverse omega n over S plus omega n square. Yeah. With our knowledge in the Laplace transform, this value is nothing but e to power minus omega nt, and this value is nothing but omega n will be here, and then S plus omega n squared, so it will be t, then e minus omega nt. Yeah. So it will be equal to 1 minus e to power minus omega n t multiplied by 1 minus omega n plus omega nt. So this is what the CT will be. Okay. In this case, we can find out the error. So ET equal to RT minus CT, and what you get is e to the power minus omega nt 1 plus omega nt, and error is steady state. We can find t tends to infinity, and what we get is this will be 0, right? So omega nt, so if t tends to infinity, whole things will become 0, so we get steady state equal to 0. Yeah, so that's what we get from here. Now we have the third case, and which will be overdamped condition. That means zeta is greater than 1, and we apply this one. So CT will be equal to 1 minus L inverse, and then we have S plus 2 zeta omega n divided by and you have S square plus So s square plus, so you get s plus zeta omega n square, right? And then you get minus zeta square omega n square plus omega n square, right? However, since zeta is greater than 1, we can write it like 1 minus inverse Laplace transform s plus 2 zeta omega n divided by, we can write s plus zeta omega n square minus, and then we write minus zeta square minus 1 omega n square, right? Since zeta is greater than 1, so this will be positive number. Yeah, we write like this, is equal to 1 minus L inverse, and we will have two parts of this. So we can write it as L inverse and then s plus 2 zeta omega n, and here we write s plus zeta omega n, and here plus root zeta square minus 1 omega n will be one part. Second part will be s plus zeta omega n minus root zeta square minus 1 omega n. So we will like this. This is the way we did earlier also, and will be equal to 1 minus L inverse, and we can write this as okay, so 2 zeta omega n, so we can write this one like this, s plus 2 zeta omega n, we can write this plus zeta omega n plus root 1 zeta square minus 1 plus right zeta omega n minus root zeta zeta omega n, here omega n also, here omega n, here also. Okay. I think it is not so simple to just work out this way. I thought by doing this I will be able to get this value correctly, and so we will get the factors very easily. But I think instead of doing all these things, what we should do is just we write the whole thing equal to a over this term. So we get s plus zeta omega n plus root zeta square minus 1 omega n, and plus we get here p over another term s plus zeta omega n minus root zeta square minus 1 omega n. Okay, so now next thing is find out these values. What we know here is a s plus bs here, so a plus b equal to 1 we get, and hence we can say b equal to 1 minus a, right? Second thing is what we get a times, so we get a times zeta omega n minus root zeta square minus 1 omega n plus b zeta omega n plus root zeta square minus 1 omega n is equal to 2 zeta omega n, right? Okay, so we will put b equal to 1 minus a. So what do we get here? We get a zeta omega n minus root zeta square minus 1 omega n, then plus 1 minus a times zeta omega n plus root zeta square minus 1 omega n equal to 2 zeta omega n. and a minus a here, so we write here a, and then zeta, omega and zeta will cancels out, this minus becomes 2 of them, so minus 2 zeta square minus 1 omega n, that's we get, and plus we get the whole thing, this one, and this one is zeta omega n plus root zeta square minus 1 omega n is equal to like this, yeah. This is equal to 2 zeta omega n, and then what do we get? From here we get a is equal to, so zeta omega n minus zeta omega n minus, so we can write omega n in common, and we have zeta minus root zeta square minus 1, so omega n zeta minus root zeta square minus 1, okay, divided by minus 2 zeta square minus 1 omega n. So what we get? Omega n cancels out, and we get minus value first of all, and then we get 1 over 2, and then we get zeta minus root zeta square minus 1 divided by root zeta square minus 1. So this is what the value of a is, yeah. Okay, so the value of b, let's find out from here. So a is this one, so b is nothing but 1 minus a, so b becomes 1 minus a is equal to 1 plus zeta minus root zeta square minus 1 divided by 2 root zeta square minus 1, and which is equal to zeta plus root zeta square minus 1 divided by 2 root zeta square minus 1, yeah. So these two values we get a equal to this and b equal to this, and the same value we can put it here, yeah, and we can solve it. So once we have the value of a and b, we can put it here, and we can find it. So equal to 1 minus, and a value we have this, so we can have a value out. So what we get is a 1 minus a, and this value is nothing but e to the power minus omega n times zeta plus root zeta square minus 1 t, and minus here also minus, so minus b times e to the power minus, and you have omega n term here, omega n, and then you have zeta plus, here we will have plus minus in this case, sorry, minus plus, so this the value will be zeta minus root zeta square minus 1 omega n t, okay. So where, so it will be like this, where we can write a value and b value now. So 1 minus a value is this, so we can have minus plus, so we have zeta minus root zeta square minus 1 divided by 2 root zeta square minus 1 e minus omega n zeta plus root zeta square minus 1 t, and then you have minus here but positive here, so minus b value is this, so we'll have zeta plus root zeta square minus 1 divided by 2 root zeta square minus 1 and e to the power minus omega n zeta minus root zeta square minus 1 t. So this is what we get Ct. Okay, so this is for overdamped condition, right? Okay, now we can find out the error basically. So we have the value here, and so RT error ET equal to RT minus CT, and RT is 1 minus this one, right? So minus everything. So basically the RT minus CT we get like this. So will be equal to minus of this and then plus this expression. So okay, where equal to 1 minus Ct, where Ct is given by this one. Now error steady state, what we'll get, one term is not there, this term is there, so what we get, so this C zeta plus root zeta square minus 1, so this is positive number, all the positive number, here is a negative, so total thing is negative. So at t tends to infinity, this becomes 0. Here zeta minus root zeta square minus 1, so zeta square minus 1 is less than zeta square, hence zeta minus root zeta square minus 1 is a positive number. So this also is positive number, and from here to here, so total thing is a negative number, and hence with t infinity this will also will be 0. So what you get in that case is tends to will be 0. Yeah. So in this case also what we see is the steady state error will be 0, but it may take longer time to achieve RT. Yeah, so this thing we will see in the next lecture video. Okay, so where we will compare the performance, meaning that the error in all the cases, how it is with respect to the time, which one goes faster, becomes we have three conditions, right? So we have like underdamped, critically damped, overdamped, all the three conditions, which one is going to be achieving RT fast. So we are talking about CT. CT is the outputs. So how long for CT is to achieve RT? Which one is the faster way? That we will see. Yeah. Okay, that is all for today.